Hey guys, Mr. Backerberg here. In this video, we're going to look at learning about functions from their derivatives. So we can figure out almost everything we need to know about a differentiable function y equals f of x by examining its derivative. We can determine where the graph rises and falls. We can figure out the local extrema. We can differentiate that derivative to learn about the concavity and how the graph bends as it passes over those intervals where it's rising and falling. We can determine the shape of a function's graph. The only thing we really can't figure out is where to place the graph on an x and y plane. In order to do that, we would need to know a specific point on the graph of the original function f. So there's a lot of things that we can figure out graphically based on knowing information about the derivative or the second derivative of a function. So in this top left-hand corner, if we know that our function is differentiable, then that means that we have to have a smooth connected curve, and the graph could rise or it could fall. Now, knowing that the derivative is positive, we know that the graph has to rise from the left to the right. Now, there could be some waves in there, but it has to increase from the left to the right. Conversely, if we know the derivative is negative, then the graph has to fall from the left to the right. Now, talking a little bit about the second derivative, if the second derivative is positive, that means that our graph is concave up. There's not going to be any waves in there, but the graph could be going up or it could be going down, but it still has this concave up look to it. Versus if the second derivative is negative, then we've got this concave down look. And again, your graph could be rising or it could be falling, but it's still got this concave down look. Now, anywhere the second derivative changes signs, that is a point of inflection where your graph changes its concavity. Looking at maxes and mins, if your derivative changes signs, then we've either got a local maximum or a local minimum. It'll be a local maximum if we go from positive to negative, and it'll be a local minimum if we go from negative to positive. Now, any points where your derivative is equal to 0 and your second derivative is negative, that's another way that we can figure out that a graph has a local maximum. Or if your derivative is equal to 0 and your second derivative is positive, then that's going to tell us that our graph has a local minimum at that point. Now, one thing we do want to keep in mind is that a function could be continuous and still have points of non-differentiability if there's a cusp or a corner or a vertical tangent. So we might have a non-continuous derivative, but that could lead us to having a continuous graph for our function f. So in this example, we're going to be taking a look at a discontinuous derivative. So here's what we know. We've got a function f that is continuous on the interval from -4 to 4, but the discontinuous derivative with a domain of -4 to 0 and 0 to 2 and 2 to 4 is shown in the graph on the right-hand side. We want to figure out all the x coordinates of the local extrema and also points of inflection for the original function f. For the extrema, we're going to look for any places where the derivative changes signs. As we read our graph from left to right, right here at the x value of -3, our derivative goes from being positive to negative, so we're changing signs there. Then at -1, we go from negative to positive, so again, we're changing signs there. Then at the x value of 0, we're actually changing signs here. On the left-hand side, we're up with positive values, and then on the right-hand side, we've got some negative values there. So even though our derivative isn't continuous there, it's still changing signs at that x value of 0. Then at 1, we're changing signs again, so we're going from negative to positive. And then again at 2, again, our graph is discontinuous, but we jump from being positive down to being negative as well. So there's 5 places where we've got sign changes: at the x value of -3, at the x value of -1, at 0, at 1, and at 2. So now let's talk about what each one of those extreme values are. Now, any place where our derivative changes from being positive to negative, that's going to create a local maximum. And there's a few places where that happens on our graph, starting with -3. On the left-hand side, it's positive. On the right-hand side, it's negative. So that has a local maximum at -3. But also, as we look at this x value of 0, it was positive on the left-hand side, but negative on the right-hand side. So that also is going to give us a local maximum there. And then as we look at that x value of 2, positive on the left, negative on the right, so that's also going to give us a local maximum. So we've got 3 local maximums happening. Now, as far as local minimums, a local minimum happens anywhere where the graph changes from being negative to positive. So first at this x value of -1, it's negative on the left-hand side and positive on the right-hand side. And also at this x value of +1, it's negative on the left-hand side, positive on the right-hand side. So we've got those 2 local minimums. So those are the places where we can see extreme values from sign changes in the graph, but there's going to be a couple more extreme values. And what we need to look at is, because this is a closed interval for the domain of our original function, we also need to check the endpoints. So we need to look at what's happening at the end value of -4 and also what's happening at the end value of +4. Now with -4, because it's a left endpoint and our derivative is positive, that's going to create a local minimum there. And then at our right endpoint, because our derivative is negative there, then that's also going to create a local minimum. So this one actually has 4 local minimums once we consider those endpoints as well. Now, as far as points of inflection, those happen anywhere where the derivative changes directions. And there's only one place that we have to worry about in our picture. And I'm looking at this x value of -2. Our curve changes directions in there. So we've got a point of inflection happening at the x value of -2. So now what we're going to do is take that picture of the derivative and that information that we just talked about and try to sketch a possible picture for our function f. Now, one thing that we talked about was at that end point at -4, we were going to have a local minimum value. So I'm just going to pick some point to start at. So maybe I'll start right here with my function. That's going to be a local minimum, and then we have to go up from there. As we look at the derivative is positive. So that means that my graph for the function has to be increasing. But what else I notice is that the derivative itself is decreasing. It's going down. So as I draw my increasing function, it has to be concave down. Then at the x value of -3, we said that that was going to be a local maximum. So this graph is going to have to round at the x value of -3 and have a high point there. Now, because our derivative keeps decreasing, our function is still going to be concave down on that interval. But then once we hit this x value of -2, our graph changes its concavity. So it was concave down, but now we need to start swooping the other direction to be concave up. And then again, at the x value of -1, our derivative is changing signs again there, going from negative to positive. So that means we're going to have a local minimum at -1. And then our graph will have to turn and go up from there. Now this time our derivative is increasing, so we want our graph to be concave up. Now if we look at what's happening at the x value of 0, our derivative changes signs, going from positive to negative. But the derivative so that means we're going to have a local maximum there, but the derivative is discontinuous. So that means that the derivative doesn't exist at this point for some reason. Now I notice the different slopes on either side of this derivative, so that's going to tell me that our graph is coming to a cusp at the x value of 0. Now directly to the right of 0, our derivative is negative, so that means that our graph has to be coming down until we hit that x value of 1. So because we're negative on the left of 1 and positive on the right of 1, we've got a local minimum happening at the x value of 1. So our graph is going to have to change directions in there. Then at the x value of 2, again, we've got a discontinuity happening within the derivative. It's positive on the left and negative on the right, meaning that there's going to be a local maximum there. And then to the right of 2, I notice that our derivative stays constant there. So a constant derivative means that this is going to be a straight line heading downward. And then we'll stop at that x value of 4. So again, this is just a potential sketch of our graph based on the information that we knew from the derivative. That's going to be it for this video. Thanks for watching.